Hello, everyone. Come on in. You have any questions? You can ask them now while we're waiting for other people to come in. I'm going to check, make sure my screen sharing is working properly. Looks like it is. Come on in, Joseph. So, anyone have any questions about anything? Well, looks like we don't. That's cool. I want to remind everybody I should have a practice test made up today, tomorrow, or Friday. And I also should have a regular test made up by then as well. So whatever day that's made, I'm going to give you a week, which would include obviously that day plus the next 6 days for you to take the practice test and take the online test as many times as you want. So if I get it made by Thursday, which tomorrow, that means your test will be due Thursday, but I will also in that intervening period before Wednesday, which next week, before that, I will have the practice or the retest midterm up as well. And I'm going to give you all of Thanksgiving break plus probably till Wednesday the week after to make sure you have plenty of time to do your retest of your midterm. Again, not required to do it, but it's optional, and it's an option such that if you do better or do worse this time than you did the first time, I'll let you keep your first score. And still, it remains that if you do better on the final than this, then I'll give you the final grade for it. So it's no downside to taking it. You only get one chance, but it'll give you more chance to study. I found out some students were having problems accessing their midterm that they've already taken. So I found a way I could do that. I don't know if this class was one of them, but because I have so many classes, but I just went and set them all to the same setting. Some are already set to that, but basically you should be able to click on your midterm test either in the module that says face-to-face test or in the actual your grade book. You can click on the score there, and it should allow you to see the questions that were on the midterm, as well as all the answer choices, as well as your answer choice and what the whether it was right or wrong. It won't tell you the right answers if you got one wrong, but you might be able to find someone else that has the right answer. So feel free to use our discussion boards accordingly. So now that I got all that out, does anyone have any questions? I literally just walked in the door from my day classes, so didn't get much time to prep. The good news is I prepped for this class earlier, so we're pretty much doing the same thing that we do in 241 during lecture. So today I'm going to go ahead and I've actually spent more time on special relativity than I had planned, because I looked at the number of days we had left in our schedule and stuff like that and realized that we're really not in that bad of a situation. So I wanted to go ahead and cover that. And then when we get back, we'll probably do essentially all of 14 on the Monday, I guess, or yeah, you guys will be Monday, and then all of 15 on Tuesday probably. And then the following weeks after Thanksgiving, you don't have much time, but basically you'll have the time to maybe do a little bit of quantum mechanics, or excuse me, for your case, it'd be a little bit of elementary particle physics. So we should have plenty of time, in other words. So with special relativity, I'm going to give you a little bit of information regarding general relativity as well. That was the area that I was most interested in as an undergraduate, and when I was working on a PhD, that was the area of expertise that I was working in. Hardly am an expert, but I did, understand the basics and have a pretty good grasp of it. I haven't done it in a while, so it's not that fresh, but still, I love the work. What I thought I'd do first is go ahead and calculate, for instance, the momentum of an electron and compare it to the classical version of the momentum for two different scenarios. So first off, we're going to imagine an electron moving with a velocity of 4 times 10 to the 7th meters per second. So remember, the speed of light is about 3 times 10 to the 8th. So this is a little bit less than or a little bit more than 1/10 of the speed of light. And then we'll do the classical version, which is just MV. And then we'll do it for 0.98 C and see how much they differ. So let's get started on that. I'm going to start by sharing my screen. Okay. See what's happening here. Should be good. That's good. All right. So what is the correct and classical momentum for an electron A traveling at a speed of 4 times 10 to the 7th, I'll say 4.00 times 10 to the 7th meters per second, and B 0.98 C. Okay, so that's our question. I do know that the mass of the electron is 9.109 times 10 to the negative 31 kilograms. And I know that C is technically 299,792,458 exactly meters per second. As we talked about before, of course, the length of the meter was defined in terms of the speed of light. So that's why it's exactly that now. So let's start off with part A, solution. So on the solution for part A, what we see is P is equal to gamma MV. That's the relativistic formula. So I'll write that up here too. P equals gamma MV. And P classical, which I'll put a C on, is MV. So in this case, we're going to say mass, which is 9.109 times 10 to the negative 31 kilograms, times 4.00 times 10 to the 7th meters per second. All that is multiplied by gamma, and gamma is 1 over the square root. So this will be 1 minus 4 times 10 to the 7th over 3 times 10 to the 8th squared. Okay. Now, in this case, we're going to get 9.109 Whoa. Somehow I hit answer before, so that was going to give me a really bad answer. So this is actually equal to 3.64 times 10 to the negative 23, and that is kilograms meters per second, and then all that divided by, if I take 4 e to the 7th and divide it by 3 e to the 8th, I get 1.33333, and then when I square that, oops, I'll say I'm going to get the square root of 1 minus 0.01778. That's the square. Okay. Now you might, and Yeah, that's about right. So if I put a negative on that and then subtract it, so hold on, somebody else is coming in. So I'll put a negative on that and then add 1 to it. So I'll say 1 minus 0.017777778, like that. And then I'll take the square root of that. So this is going to be 3.64 times 10 to the negative 23 kilograms meters per second divided by 0.99107, say. So basically, I'm going to take divide that out, and I get 3.67 times 10 to the negative 23rd kilograms meters per second. So notice that's the classical version. So this is P, which is the correct version. And since the P classical version is just equal to M times V, notice that's just the numerator in that expression that we already wrote. So I'm going to write that that's 3.64 times 10 to the negative 23 kilograms meters per second. So you can see there's not a huge difference. Basically, if you wanted to, for instance, calculate the percent error, it would be 3.67 minus 3.64 over 3.67 times 100, and then put a percent symbol on it, and you get 0.03. That gives me about 0.82%. So yeah, that's not that big a deal at that speed, which is pretty surprising because that speed's pretty high. Like I said, it's better than 10% of the speed of light. 10% of the speed of light would be basically 2.99 times 10 to the 7th. And this is 4.9, or this is 4 times 10 to the 7th. So it's a little better than that. Now let's try part B. Anybody have any questions on that before I go on to part B? Okay, part B, use the same formula, except we're now using a different value of the speed. In fact, the speed is going to be 0.98 c. So when you write that gamma is 1 over the square root of 1 minus v over c quantity squared, if I put in 0.98 c for the v, then the c in the v term is going to just cancel out with the c below it. So I'll end up getting, again, 9.109 times 10 to the negative 31 kilograms. Now, this time, they didn't give us an exact velocity. They gave it to us in terms of the speed of light. So I got to write that percentage, or that decimal, 0.98. And then I'm going to write 3.00 times 10 to the 8th meters per second. So if you notice, that numerator is again the classical momentum, but this is going to be 1 minus 0.98 quantity squared, like that. Okay, so again, because it's v over c, the 0.98 c over top of c makes the c's cancel out, and this will give me 9.109 e to the negative 31 times 0.98 times 3 exponent 8. That gives me 2.67. I actually call it 2.68 times 10 to the negative 22 kilograms meters per second is for the numerator. And then I'm dividing that by the square root of 1 minus 0.98 squared. So that gives me the square root of 0.0396. So I'll take the square root of that. And then I'll do 2.6780 e to the negative 22 divided by 0.198997, say. That's roughly what the square root came out to be. And this gives me 1.35 times 10 to the negative 21 kilograms meters per second. Now notice in this case, if I divided that 1.35 times e to the negative 21, if I divided that by the classical, which is a 2.68 times 10 to the negative 22, I get 5 times. So in fact, P classical is equal to 2.68 times 10 to the negative 22 kilograms meters per second, which is literally 5.03, actually 5.04 times smaller than the actual P. So you can tell it's actually very, very important when you get to that high of a speed that you do the correct formula. Now, a rule of thumb that we often use is if the kinetic energy of the particle that you're dealing with, or the thing that you're dealing with, if that kinetic energy is comparable to the rest energy of the particle, then you should probably use relativity. So right now we're dealing with an electron, and it turns out an electron has a rest energy of the mass of the electron times c squared, which is not very big in joules, but what we find is E electron is m sub e c squared. And if I convert that to electron volts, it's 511 kilo electron volts. So if you convert it to electron volts, then that's the easier way to confirm. But if I want to take 511 e to the 3, and if I wanted to take that and multiply it by 1.602 e to the negative 19, that's the conversion between electron volts and joules, then I get that that is 8.19 times 10 to the negative 14 joules. So that's the kinetic energy of the actual, or excuse me, that's the rest energy of the electron. If you wanted to know what the kinetic energy of the electron was, that's supposed to be gamma minus 1 times 0.51, or excuse me, times 511 kilo electron volts, or gamma minus 1 times 8.19 times 10 to the negative 14th. So you could compare that if you wanted. But basically, you would find that this second case B, you definitely have to have the proper relativistic mass, relativistic kinetic energy and momentum. So that's the formula for kinetic energy, is that gamma minus 1 in parentheses times MEC squared. All right, so that's just a pretty straightforward calculation. Anybody have any questions on that? So the next thing I want to do is I want to find out whether special relativity is important enough to take into consideration when I use a GPS satellite. So I'll start it this way. A GPS satellite uses an atomic clock that has a fractional that was just ugly. A fractional. Oh, I left off a whole letter. No wonder it came out so bad. Uncertainty of, let's say, delta t. All right, let's not say it that way. Let's say sigma t over t is 1 over 10 to the 13th, which equals 10 to the negative 13. How does delta t minus delta t0 over delta t0 compare to sigma t over t? So that's really the big question: is it comparable? Because if it is, if this delta t over delta t0 minus divided by delta t0, if that's bigger than 10 to the negative 13, then yeah, we've got problems, because we've got to take into account special relativity. So let's calculate that. Well, it turns out a GPS satellite whoa, what happened there? A GPS satellite travels at v on the order of 4.00 kilometers per second, which of course is 4,000 meters per second. That's a pretty small velocity compared to the speed of light, but we need to know. So what we know is that delta t, the time that's not proper, this is the time of an observer that thinks another observer is actually moving by them. That time is given by the proper time divided by square root of 1 minus v over c squared, like this. Okay, remember gamma is technically 1 over the square root of 1 minus v squared over c squared. So what we're going to do is write our solution. Should have wrote that before I wrote that equation, but oh well. So I'm going to write our solution. I'm going to say delta t is equal to delta t0 over the square root of 1 minus 4 times 10 to the third over 3 times 10 to the 8th. And that'll be squared, right? Which is delta t0 over the square root of, now 4/3, let me see, 4 e to the 3 divided by 3 e to the 8 should give you 1.33 times, 10 to the negative 5th. So 1 minus 1.333 times 10 to the negative 5th. And then that quantity's got to be squared. So I can write this as this. I'm going to say delta t0 times 1 minus, now I'm going to square this number that I just calculated, the 1.33 times 10 to the negative 5th. I'm going to go ahead and square that. And I'm going to say this number is 1 minus 1.77 times 10 to the negative 10th. And this whole thing is raised to the negative 1/2 power. The reason I'm doing that is because you're going to have a little bit of a difficult time actually processing that, because that one, can put any number of zeros after the decimal point, and that's just fine. But then you're going to subtract 1.77 times 10 to the negative 10, and your calculator is going to tell you that's 1. Okay. If you have a really, really big screen calculator, they might tell you it's 9999999, 0.9999 or something got off like that. Actually, yeah, something like that. So what we're going to do is we're going to use the binomial theorem, which basically says that if you do a Taylor series or Maclaurin series expansion on 1 plus or minus x raised to the n power, then you get, there's more terms in this, but it's 1 plus or minus n times x are the first two terms. And this is for x much, much less than 1. Notice the expansion would have you have next to n times the n minus 1 times x squared over 2 factorial. The next term would be a n times n minus 1 times n minus 2 over 3 factorial times x cubed. Now you see this x is like 1.33 times 10 to the negative, or excuse me, 1.77 times 10 to the negative 10th. You can imagine that if I cube that or square that, that's a really insignificant amount. So really these first two terms are the most important ones. So that's why I just wrote the first two terms, because there's really not much need to do the other ones. Okay, this is n to the x and this is plus or minus. So notice also with this formula, the top sign is plus, so is the top sign on the right hand side. So that means basically whatever sign you have as your x, as your in front of the x is the same sign you used before the nx. So in this case, I want to say 1 minus 1.77 times 10 to the negative 10th raised to the negative 1/2 power is in fact equal to 1 minus negative 1/2, because that's the power, times 1.77, which actually I guess I should call that an 8 to properly round it because it's all sevens, times 10 to the negative 10th. Okay, so when I do that, I can actually make some sense of it. I'm going to say 1, and actually since it's minus and negative, it's going to be plus. So plus 1.78 e to the negative 10. And that gives you basically a flat 1. Again, with the calculator. But it really gives you 1 plus 0. Whoa, what happened here? Oh, I forgot something. Hold on a second. 1 plus 0.5 times 1.78 e to the negative 10. Okay, that looks right. It's basically 0.000000000. That's 10 to the negative 9th. And then 10 to the negative 10 would be there. And then there's an 8, and then there's a 9. Okay. So it's 1.0000000000089 is what that gamma factor is. So now we can calculate delta t minus delta t0 over delta t0. Delta t, we've just found in terms of delta t0 is 1 plus 0.0000000000089 times delta t0 minus delta t0, all of that over delta t0. So we're really fortunate in that the one that comes from the second term in the, or the third, depending on how you count it, the second or third term in the numerator, that one is going to cancel out with the first one. So on top, you're just going to be able to have a delta t0 that you can factor out, and then a delta t on the bottom. So those two cancel out completely. So you end up getting just 0.0000000000089. That's the whole quantity, which is in fact 89 over let's see, if I wanted to make it 89, that's 3, 6, 9, 12. So that's over 10 to the 12th, which is in fact greater than 1 over 10 to the 13th. It's in fact quite a bit greater. You could multiply it by 10, and that would get you 10 to the 12th in the bottom. And then you could multiply it by 89. And so it's basically 890 times bigger. So yes, special relativity is required for GPS. Now, here's the neat thing. So I've told you we're going to talk a little bit about general relativity, and this is the start of it. So it turns out, if you take into account the special relativity as we did there, we do see that the error is too big. It's basically 890 times bigger than the uncertainty in our cesium-137 clock that's going around in the satellite. So we need to account for that. It turns out that due to special relativity, that means the GPS, because it's up there going really, really fast, its clock is moving slow compared to Earth. And it frequently tells us, time, like when it sends out a signal, the GPS satellite, when it sends out a signal, it's giving us the time that the signal was sent out. But because it's moving, its clock is running slow. And we need to be able to correct for that so we can know exactly what time it was sent in our reference frame. And then we can multiply that time times the time difference between our time in receiving it and our time in getting it. We can multiply that by the speed of light, and then that'll give us how far away we are from one of the satellites. Generally speaking, you have to have at least 3 satellites, and when you get 3 satellites, the distance between all of them. There's only one answer that gives you the correct distance. So that allows you to find exactly your position with respect to those 3 satellites. Now, the way the satellites are designed is that they're not in geosynchronous orbits. They're actually in orbits that are about 12-hour orbits. So they cross the surface of the Earth or go around the Earth twice a day. And the reason they did that is they set it up so that you would always have, no matter where you are on the Earth, at least 4 satellites visible to you from any spot on Earth at any time of day. And sometimes you can have as many as 12 GPS satellites visible to you. So doing that, you're basically guaranteed that you're going to have 4 satellites, and you need 3 as a minimum to get it right. And a 4th one can allow for 1 to be down, or it can also allow as a double check. So because that clock is running too slow because of its velocity, it turns out that special relativity says GPS clock loses about 7 microseconds per day. Okay, that's not very big, but again, we're talking about 10 to the negative 13th. So that's literally way smaller than micro. Nano would be 10 to the negative 9, and femto would be 10 to the negative 12th. I think that's femto's next. Anyways, micro, nano, no, pico is 10 to the negative 12, femto's 10 to the negative 15. So it would be on the order of picoseconds. So yeah, that's important. Now, the neat thing is general relativity is also an issue. And it turns out that general relativity says, hey, gravity is not a force. In fact, Misner, Thorne, and Wheeler in the book Gravitation, which is sort of the Bible of general relativity, it was written in the mid or late 70s. And it was basically everything we knew about general relativity in 1974. And Charles Misner, John Archibald Wheeler, and Kip Thorne wrote that. Kip Thorne was one of the 3 guys that just won the Nobel Prize for detecting gravitational waves from a binary black hole collision. So he's a bigwig. Wheeler had already died, so he didn't get it, and Charles Misner had already died, so he didn't get it. I do have the distinct pleasure to announce that my PhD advisor wrote, I think it was chapter 27 of that book. So that it's called York's Handles on Gravity, and that was my PhD advisor, although I am ABD. So anyways, with regards to general relativity, what general relativity tells us is basically that when you're inside of a gravitational well, like the satellites up here, we're down in the gravitational well on the surface of the Earth, then that means our clocks will run slower just by being at a lower point of gravity. It's like we're moving really fast because we're close to the Earth. And the farther we are away from the Earth, but still, relatively located, like geosynchronous or something like that, then the slower our clock goes and the faster their clock goes. So because of that, the actual special relativity is causing us to lose time, but general relativity is causing the GPS satellite to gain time. So GR says GPS satellite gains about 45 microseconds per day. So not only is general relativity relevant, it's actually way more relevant than special relativity. So ultimately what they have to do is they subtract about 38 microseconds per day from a GPS satellite, because 45 is how much you go over. It's how much you go fast. 7's how much you go slow. 45 minus 7 is 38. So that's sort of some relevant materials. Now, you could actually track down this error that I just found, the delta t minus delta t0 over delta t0. You could use that to estimate basically how much time you'd lose. And if you do that properly, you should come up with somewhere close to 7 microseconds over a 24-hour period. So that they're related in that sense. None of this figures, so these calculations that I did, none of those gave you that data. So I just want to make sure y'all knew that. Any questions on that one? Remember that binomial thing. That's something I wanted to make sure you guys knew anyways, because that's a common technique in physics and engineering, is sometimes you just have a number that's way farther off than 1, and you're subtracting it from 1 or adding it to 1 or something like that. And really just about the only way you can deal with it is use the binomial theorem. And like I said, in the back cover of your book, it has it written out to like 4 terms, I think. And once you see the second and third term, the third and fourth term, you'll know exactly what the pattern is. It's pretty trivial. So no questions? I did something good. Y'all are going to be very happy. I set my alarm to remind me. I used to have it at the beginning of the semester. I guess I turned it off by accident, but it's going to remind me when it's 2 till time for you guys to get out. So I won't keep you over this time. What I want to do now is I want to give you a calculation of kinetic energy of a particle. So let's say a pi 0 particle m sub pi 0 is equal to 2.4 times 10 to the negative 28 kilograms, is traveling at beta equals 0.80. What is its, actually, I almost put an apostrophe on that. Whoa. What is its correct kinetic energy and K classical? Okay, so the formula, go ahead and write this out now. Solution. To find out the solution, we need to know the formula for kinetic energy. The correct formula for kinetic energy is gamma minus 1 times mc squared. The classical kinetic energy is 1/2 mv squared. Okay, and remember, beta is defined to be v over c. So that's why there's no c after the 0.8, because that's what we're doing here. So now let's look at what gamma is. Gamma is equal to 1 over the square root of 1 minus beta squared, which equals 1 over square root 1 minus 0.80 squared. Now, 8.80 is really 8 over 10. So if you square that, you're going to get 64 over 100. And then you're going to say, okay, well, this is 100 over 100 minus 64 over 100. And because of that, you get 1 over the square root of 36 over 100. So you know already that gamma is in fact 10 over 6. Okay. So that's kind of nice. We know that 10 over 6. And in fact, if you take 10 and divide it by 6, you got 4 left over, and 4 over 6 is the same thing as 2 over 3. So it'd be 1.6666. Ooh, eraser stayed there a little too long. Okay, so that's what our gamma factor is. So now I can say the kinetic energy is equal to 1.666 with a bar over it minus 1 times, now I'm going to write 2.4 times 10 to the negative 28 kilograms times c squared. So this is 2.99. Let's go ahead and go a couple extra digits, 792 times 10 to the 8th meters per second, and then squared. Notice I'm using c, not velocity, because that's what the formula says. So I'm going to do okay. Minus 1. Obviously, this is going to give me 2/3 right here. That's 1 and 2/3 minus 1. So that's just 2/3. And then 2.4 e to the negative 28 times e to the 8. That gives me 2/3 times 7.195, carrying an extra digit basically, times 10 to the negative 20th. And that's joules. That's the MC squared. That gives me 4.7. Actually, I should call it 4.80 times 10 to the negative 20 joules. This is a good time for us to compare it in electron volts. So this is 4.80 times 10 to the negative 20 joules. But if I multiply that by 1.602 times 10 to the negative 19th, actually divide it by 1.602 times 10 to the negative 19th joules per electron volt. Then I get 0.299 electron volts. Okay, so that's another way of looking at it as energy. It's just the electron volt. 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. And you're not really, I mean, I showed it to you a couple times before in the past, but it's not necessarily supposed to make any sense to you until next semester. That's when we learned that the potential energy is the charge times the voltage. So if you take a charge of the electrons, which is 1.602 times 10 to the negative 19th, and multiply it by a voltage of 1 volt, then you'll get the electron volt. So that's why that number doesn't look that familiar. But you can see, for instance, in this case, that the 2.4 e to the negative 28 times the muon's kinetic energy, or rest energy, let's say E rest for the pion, I think I said muon a second ago, is equal to the mass of the pion times c squared. and that gives me 2.157 times 10 to the negative 11th joules. If I divide that by 1.602, oops. Uh-oh. Okay. 1.602 e to the negative 19. That gives me a really incredibly large number, 1, 2, 3, 4, 5, 6, 7, 8. That gives me 134 mega electron volts. So this isn't necessarily a realm where you're forced to use relativity, because the energy is so much, the rest energy is so much bigger than the kinetic energy. But still, let's look at the classical kinetic energy. So the kinetic energy classical is 1/2 mv squared. That's going to be 1/2 times 2.4 times 10 to the negative 28 kilograms times 0.8. I'll put a square bracket around that, 0.8 times 3 times 10 to the 8th meters per second. And then the square bracket will be squared. And I hate what I did with that 8 there. So okay, let's see what I get now. I'm gonna get 0.5 times 2.4 e to the negative 28 times parentheses 0.8 times 3 e to the 8th, close parentheses, square that. This gives me 6.9. Ten to the negative 12th joules. And our kinetic energy came up to be 4.80 times 10 to the negative 20th joules. That's a big difference. Okay. So not really sure what happened with the rest energy deal with that. But anyways, we now have the answer, which is the kinetic energy of the pion is 4.80 times 10 to the negative 20th, whereas the classical kinetic energy, 1/2 mv squared, is actually equal to 6.91 times 10 to the negative 12th. Hopefully I didn't, I don't see any mistakes I made in the calculations. Everything looks fine. So anyways, that's another problem solved. Anybody have any questions on that? All right, so I've already showed you guys this in my one of the, I think I did it in maybe Monday's class. I gave you the Lorentz transformation. I also gave you the invariant interval. So I just want to rehash what that is, and you guys can actually show this to be true, and I'll give you extra credit for it. So let me rehash what it is. I'm going to draw a coordinate system. And this is going to be my x-axis, and this is going to be my t-axis, and this is my s coordinate system. Now I'm going to draw another one over here. And this is going to be my x prime axis. And this is going to be my t prime axis. And this one's moving with the velocity v this way. And this is called s prime. Now, what we had was that x prime equals x, y prime equals y, and z prime equals z, and t prime equals t equals 0. Okay, so at that instant in time, when we called started watching the system, the two origins were laying right on top of each other. The t-axis and the t prime axis were laying right on top of each other, and the x and the x prime axis were laying right on top of each other. Same thing with the y and the y prime and the z prime. With that rule, then we can get that the distance this thing has traveled, this s prime coordinate system has traveled in a time t, is really just VT. This distance right here to some point, say, that distance is called X prime, but this distance from all the way here to here is called X. So you can see that X is equal to, at least in Galilean relativity, should just be equal to X prime plus VT. But it turns out in relativity, you have to correct it by putting that gamma there. Y, and by the way, in Galilean relativity, there's no difference between T and T prime. So I wouldn't have a prime on that T, but in special relativity, you have to. So Y turns out to be equal to Y prime because that motion is perpendicular to the velocity of the plane of the coordinate system. So it's unaffected. Same thing with Z. Z is equal to Z prime. But here's the weird part. T is not equal to T prime. And in fact, you might want to put T prime right there, but you'd have to put a gamma in front of it. And not only that, but because space and time sort of are intercommingling or whatever, we also get, notice the same sign that we had in the X equation, we get Vx prime over C squared. That's the Lorentz transformation. And if you wanted the opposite one, you wanted X prime, Y prime, Z prime, and T prime, it's not that hard. You could take the time to do the algebraic solution. In other words, solving for X and eliminating, solving for X prime and eliminating all the other variables. Or you could just be smart and use this. All you have to do is change all your primes to unprimes and change all your unprimes to primes and change your V from V to negative V. So this one's going to become X minus VT. This one's going to become Y. This one's going to become Z. This one's going to become gamma T minus Vx over C squared. So if you call, let's say, delta X, if you call that, say, X2 minus X1, where X2 just means gamma X2 prime plus VT2 prime, and X1 would be gamma X1 prime plus VT1 prime, and delta T would just be T2 minus T1, so that you get T2 is equal to gamma T2 prime plus Vx prime over C squared, and that's a 2 on that too. And T1 is equal to gamma T1 prime plus Vx prime 1 over C squared. Okay, so now I've showed you how to actually form delta X and delta T. The invariant interval is called delta S, and it has nothing to do with those S's that I use to name those coordinate systems. But the invariant interval is delta X squared plus delta Y squared plus delta Z squared minus C squared delta T squared. And since it's invariant, that means it's also equal to delta X prime squared plus delta Y prime squared plus delta Z prime squared minus C squared delta T prime squared. Okay, that's called the invariant interval. If you imagine shooting a beam of light out from the origin by a point source at t equals 0, then I think you can sort of see that the coordinates x, y, and z at any point later would be given by x squared plus y squared plus z squared is equal to c squared delta t squared. So you can sort of see what this is like. This is the difference in space and time sort of related to a light cone, but it can be used for a lot of different things. For instance, I once realized that the t prime and x prime axes can be graphed in the S coordinate system. And all I had to do was use this invariant interval to find basically where it was and how big the units were. You can use it to derive these Lorentz equations. You can use them to derive time dilation and length contraction. And you can even use them to figure out how your coordinate systems are related. So it's just a neat little thing that comes in here. And it's something that's invariant, which means no matter what interval or what coordinate system you're in, this quantity is always going to be the same. Okay. Whether you're in a coordinate system that's moving at, 7/8 the speed of light, doesn't matter. All right. So I got that. It's 6:15 now. Anybody have any questions on that before I move on? So if you all want to, you can, now that I've sort of showed you what delta X and delta T are, you can plug in that delta X, that delta Y, that delta Z, and that C squared, delta T squared. And when you plug it in, it's going to be all in terms of X primes and T primes. And if you play with the algebra enough, you'll be able to transform it into the right-hand side of that interval. And what I'm saying is that's an extra credit problem if anybody wants to do it. It's just algebra. It's not anything super complicated, but it's algebra, and it gives you a lot of good algebra practice. So no questions? I don't have my chat box up. Let me get that up just in case somebody's talking to me via chat instead of voice. All right. So no questions. All right. Another one I want to show you is let's consider, for instance, addition of velocities problem. So let's imagine we have the Earth right here, and we have a spaceship A moving this way with a velocity of A with respect to Earth equal to 9/10 c. And then we have a spaceship B moving this way with a velocity VBE. Notice everybody's got to agree that to the right is positive and to the left is negative. So VBE is actually going to be negative. And in this case, I'm going to say 19/20 c. And then not only that, this spaceship B is going to fire a torpedo, a photon torpedo, that has a velocity of the torpedo as seen by B equaling -c. What I want to find is the velocity of B relative to A and the velocity of the torpedo relative to A. Okay. So my solution is this. Anybody have any questions about this problem? Anything they don't understand or anything? So this is the same as the Galilean addition of velocities things we told you, except it's got that extra denominator. So what we found was the velocity of A as seen by C was equal to the velocity of A as seen by, say, B, plus the velocity of B as seen by C, divided by 1 plus VAB VBC over C squared. But we had the additional rule that can sometimes be helpful. Velocity of I with respect to J is equal to the negative of the velocity of J with respect to I. So I want to find the velocity of B as seen by A. That's clearly going to be the velocity of B as seen by something plus the velocity of something as seen by A. Well, I have the velocity of B as seen by Earth. So I could put that, but notice that's VEA, not VAE. We have VAE. So this is VBE, VEA over C squared. Now, VEA is just negative VAE. So there's me using that helpful hint that I told you about. So I'm now going to write this as VBE minus VAE over 1 minus VAE VBE over C squared. Now I can start putting my numbers in. The velocity of B as seen by E is -19 over 20. I'm going to factor out the c, so I'm not going to put the c next to it. And then I'm going to have minus the velocity of a as seen by c, or excuse me, as seen by e, and that is 9/10. And then all that times c in the numerator. And by the way, this 9/10 is the same thing as 18 over 20. So we can get a common denominator for the numerator. That'll be nice. Now I can go back and say 1 minus, now the velocity of A as seen by E is 9/10. And the velocity of B as seen by E is negative 19/20. And each of those were times C, and there's a C squared on the bottom. So I could say just C squared here and the C squared here, and you realize then that those two cancel out. So now we're going to get negative 19 minus 9, so that'd be negative 27. Or excuse me, scratch that. I got to get a common denominator, which is 18 over 20. I almost forgot to do that. So negative 19 minus 18 would basically be 3 short of 20 plus 20. So that'd be what, 37? Negative 37 over 20c. And then in the bottom, 9 times 10 is 90, and 9 times 9 is 81. So that should be 171. So this is 1 plus, notice the two minuses cancel out. This will be 171 over 20 times 10, which would be 200. That makes this negative 37 over 20c. And this one becomes 200 over 200. So when I add those two, that becomes 371 over 200. So that becomes 200 over 371. Because dividing by a fraction is the same thing as multiplying by its reciprocal. So now what you see is this 20 cancels out with 200, leaving just a 10. And I get negative 370 over 371 C is equal to VBA. Isn't it amazing? It just happens to be able to find, a fraction where it's just slightly less than the denominator. The numerator in this case is just one less than the denominator, and the denominator is ginormous at 310, right? So in fact, let's look at that. That's 370 divided by 371. If you actually type a 1, it's really helpful. That's 99.7305% of the speed of light. So it's pretty high, right? So yes, since 90% of the speed of light was the velocity of A, and basically 95% of the speed of light was the velocity of B towards A, you do expect the velocity that A sees B coming with to be larger than what B is moving relative to the Earth. And you expect it to be larger than VA is seeing itself going with the speed of light. And in fact, if it was a Galilean world, you would reach the conclusion that it's going to be 31 or 37 over 20 at C. In other words, 1 and 17/20 C. But relativity has the perfect little denominator in there, so it fixes it. It makes it just under the 1. So that was one part. Now what I want to do, does anybody have any questions about that before I jump to the next part? I don't see any chat. I thought I heard somebody's voice, but that could have been in another room. So here's what we're going to do with the velocity of the photon torpedo. The photon torpedo is a photon torpedo, and that's the particles that we say carry light are light. And therefore they travel at the speed of light. And as relativity tells us, the speed of light is a constant independent of the motion of the source or the motion of the observer. So if that's the case, Einstein's special theory of relativity says that the speed of light is a constant independent of the motion of the source or the motion of the observer. Then the source, namely the guy that shot the photon torpedo, should see the torpedo traveling to the left at c, and that's what we wrote down. VTB is equal to negative c. But special relativity says A should see VTA as equaling C as well. And of course, it's going to the left, so it should be negative C. So let's work that out. So what I have is VTA is equal to VTB, because I have that already. I've decided to use the B, plus VBA over 1 plus VTB VBA over c squared. Well, the velocity of B with respect to A, I've already worked out. It's negative 370 over 371. So I'm going to say negative C plus negative 370 over 371 C. All that divided by 1 plus. Now, I'm going to go ahead and cancel out the C's, but basically I'm going to say this is negative 1 times 370 over 371. Okay. And that was negative 1, and the other one was positive, right? So that was negative 1 for that one, and the other one was also negative. So I should put a negative in there as well. So you can see what happens is I get, when I go to add this C, this negative C on the top, that becomes 371 over 371. So I'll factor out a negative C, and I'll say this is 371 over 371 plus 370 over 371. Okay, so that gives me what, 841 over 371. And then down here at the bottom, I've got 371 over 371 plus 370 over 371, which gives me negative C, and this would be 841 over 371. And down the bottom, that's going to be 841 over 371. So lo and behold, I get a negative C. So relativity is right. It seems to work. Any questions on that? Okay. So this is another problem with special relativity. You now have the Lorentz transformation equations. You got time dilation, you got kinetic energy. I already told you about E squared equals P squared C squared plus M squared C to the fourth as well. So you know all that stuff. You know about the velocity addition equation, so on and so forth. So we've got a pretty good introduction to special relativity and the major things that happen as a result of it. Your book does the derivations, so you can look at those. The only derivations I did were the length contraction one and the time dilation one, but I literally used the time dilation one to derive the Lorentz contraction or the length contraction one. So I wanted to talk a little bit about relativity, and I actually got sidetracked a second ago when I was talking about the book Gravitation that I said was like the Bible of general relativity. The reason I even brought that up was I meant to tell you this famous quote in it. And this famous quote in it says that matter tells space how to bend, but then space tells matter how to move. And that's about as beautiful a statement of special relativity, our general relativity, as you'll ever hear. So let me give you an intro to general relativity. So Einstein's two principles of relativity were, one, the laws of physics are the same for all inertial observers. Special relativity had that inertial observer in there specifically, like I told you before, to get rid of the force of gravity, because he was treating the force of gravity as if it wasn't really a force. And in fact, it was something that was screwing up with the inertial reference frame, because really what was going on is things were moving in a way inconsistent with Newton's first law of motion. In other words, if you look down on our solar system, you saw our planets not going in straight lines, but going in elliptical orbits as if there was some force pulling them. But there was nothing attaching the sun to the planet. Therefore, it couldn't have been a force. That's what he was sort of implying. So when we go from special relativity to general relativity, that the laws of physics are the same for all inertial observers becomes the laws of physics are the same for all observers, period. Okay. Now, what that meant from a mathematician physicist point of view was that the laws of physics must be written in tensorial form. Okay. So you're starting right now to see a little bit of vector calculus, which is an important level of mathematics that's really helpful for electricity and magnetism. So you're going to learn a lot more next semester. But it's also just a precursor of a higher thing, which is called tensor calculus. And really, a vector is a special case of a simple tensor. Okay. So the reason why he had to reach the conclusion that they had to be written in tensorial form, he would say they had to be written in a covariant form. And what that means is there's a very specific way in which a vector, which is a type of tensor, and also a very special way in which a tensor transforms from one coordinate system to the other. It transfers, or you can transform it from one coordinate system to the other by multiplying it by a derivative matrix. In other words, you're taking a derivative of some matrices you're taking the derivative of parts of a matrix and multiplying that matrix times that vector or that tensor or whatever. And if you do that, then you will automatically always have the equation have the exact same form, no matter what coordinate system you're in. So that told him, oh crap, I remember now that math that I had the professor that called me a lazy dog. Oh yeah, that was the math we were learning there, and I don't remember it very well. So I went to see his friend Marcel Grossman, who paid attention in the class and was probably liked by the instructor. And Marcel Grossman and other people worked with Einstein to help him work out tensor calculus and make sense of it. And then he could make a covariant form of the laws of physics as he thought God would make it. And again, this is him. It sounds really sacrilegious and blasphemous and stuff like that, but you got to remember Einstein, as a person that kept making calls on God, was not seeing God the same way we do. He specifically said he believes in the God of Spinoza. So if you look up Baruch Spinoza, he's a philosopher. I want to say he's Hungarian or something, but it might not be. I can't remember where he's from. But anyways, if you read his definition of God, it's irrefutable. It's basically the God that has to exist, but he also doesn't do much, right? It's sort of the laws of nature are God for him. So it's not as blasphemous as it sounds when he says these blasphemous sounding things. So put that to the side, use it as you want, whatever. So that's the part he did with the first part, is he had to make it in tensor form. And the second part was the speed of light is a constant independent of the motion of the source and the observer. He kept that. That was part of special relativity. But there's also this thing called the equivalence principle, which is kind of weird. But the equivalence principle basically says in a small area, in a local neighborhood, for instance, you can't tell the difference between whether you're in a spacecraft that's soundproof and shooting up, accelerating upward at 9.8 meters per second every second. Because if you dropped a ball in that situation, what you'd see is the law of inertia kicking in. You just let go of the ball is going to sit perfectly still while your ship flies upward at 9.8 meters per second every second, which looks exactly like the ball falling at 9.8 meters per second every second. Similarly, if you are on that same soundproof spaceship, but the spaceship wasn't moving at all relative to the Earth, it was just sitting on the Earth. If you dropped the ball, it would fall at 9.8 meters per second every second. So that's a perfectly normal explanation. It's called the equivalence principle. But why does it say in the local neighborhood or on a small scale? Well, let me give you an example. So if this were, say, the Earth. Okay.
So you aren't sharing the screen.
Thank you. Nice catch. You got me even earlier than I did. I was just thinking it. So you beat me anyways. All right, here we go. Jamie's got to keep me tight. All right. So let's say you're on a itty bitty spacecraft, which I'm going to draw in red like that, or you're on an itty bitty spacecraft like that. In this case, it actually has an upward acceleration of a equals 9.80 meters per second every second. You would see a ball drop falling at a equals 9.80 meters per second every second, not because it was actually falling, but because it was sitting perfectly still. And the floor of your spacecraft is flying up to it with an acceleration of 9.8 meters per second every second. Similarly, this would see a ball falling at a equals 9.80 meters per second every second. So yeah, that makes sense. But he said on a local scale or on a local neighborhood or in a small scale, you can't tell the difference between an object being accelerated upward with the same magnitude as g versus an object sitting on a planet with a gravitational acceleration of g. Let me imagine a bigger spacecraft. Okay, if that's your spacecraft and you bitty bop over here and drop a ball, that ball is in fact going to fall towards the center of the Earth with an acceleration a equals g. If you do it in the middle, it's going to do the same as the other experiment. But if you do it over here, it's going to do again this way with a equal g. So by using such a big elevator or a big spaceship, you can actually discern that this is a gravitational effect as opposed to a accelerational effect. So what does that mean? That means not so much that you got to avoid big spaceships or big elevators. It really just means if I want to understand the laws of physics, I need to play with them locally. In other words, only move off differentially away, a distance dx from the position x. And that sort of tells you to use something called differential geometry. And differential geometry is really where you study geometry, but on a scale that's differential. So he can treat the universe as if it's flat and that acceleration is the same thing as gravity. When he did that, he gets his field equations, which are really nasty. They're in elliptic format, in hyperbolic format instead of elliptical format. And they're basically a set of linked, nonlinear, non-homogeneous, and partial differential equations. Like technically it's like 16 of them. Okay. Luckily, there's a lot of symmetry, so you have a little less than half of that number, but still they're simultaneous partial nonlinear differential equations. Okay, so they're butt ugly and they're really hard to solve. In fact, Einstein said when he published it, he said, we might not have solutions to these for hundreds of years. And a guy by the name of Schwarzschild, who was literally on the battlefield in World War I, literally mailed in a solution to it within a week of his publication. And he had what's called the Schwarzschild solution, which is basically a black hole sort of scenario. He just assumed spherical symmetry and worked all that out. Now, when Einstein presented this paper, he had these field equations, and the field equations were telling him that the universe was expanding. He'd never heard of such data, and he didn't believe God would have the universe changing over time. So he forced a constant, a capital lambda in it that he called the cosmological constant, and he forced it in there just to make the universe static so that it wasn't expanding. And he called that the greatest blunder of his entire life. George Lemaitre, and before him, Alexander Friedman from Russia, which Russia's having all sorts of crap going on right now, the Bolshevik Revolution and all that good stuff's going on. So anything that happens in Russia, nobody hears about for years. But Alexander Friedman took Einstein's equations and said that they were predicting the universe expanding. George Lemaitre, a Jesuit priest, did the same thing and wrote to Einstein. And Einstein told him, your math is correct, but your physics is abominable. Well, it turns out several years later, Hubble using the Hubble Space, or excuse me, not using the Hubble Space Telescope, using the telescope in Hollywood, basically, the mountain with the Hollywood on the side of it, using that telescope, he looked at the Andromeda Nebula, as it was known then, and found out it was another island of stars. And he saw other quote unquote islands of stars, and he realized there were more than one galaxy, and Andromeda was one of them, and all these other ones were one of them. And Andromeda was like 2.5 million light years away. He thought it might be 100,000 light years away because he didn't have his measurement techniques down pat yet. But all of that was by a CFID variable that was actually worked out by a female astronomer whose name I always botch, so I'm not going to try to even remember it or say it this time. But she really was the bomb. So, anyways, what he found is if he found Andromeda moving away from us at say 100 meters per second, if he found one 5 billion light years away, that would be moving at 200 meters per second. And if he found one moving at 10 million light years away, he would find that moving at 400 meters per second. And that predicted the expansion of the universe, which was just what George Lemaitre had predicted. So that was ultimately his equation, field equations, doing what they predicted space would do. And what Einstein discovered was gravity's not a force, but rather space is four-dimensional. So you got left, right, that's one dimension, in, out, that's one dimension, up, down, that's one dimension, X, Y, Z. Well, time is a fourth dimension, and it is actually perpendicular to those other three, but we don't see 4D, so it doesn't make it work very well. But in that four dimensions, it turns out that mass of, say, our sun causes a depression in four dimensions, not unlike a bowling ball on a trampoline. And then if you shoot a marble, which would represent a planet, towards sort of the edge of the bowling ball, not towards the center, then it's going to go in that well and spin around like this. And if it wasn't for friction, it'd do that forever. So what's going on is not that there's a force of attraction between the bowling ball and the marble. It's actually that the space that it's on is making the marble go in an ellipse or a circle because space is bent. So that's the general theory of relativity. He made two major predictions right on the spot. One was the aberration of starlight, which Arthur Eddington confirmed very shortly thereafter. And then the other one was his theory predicted the precession of the perihelion of Mercury, which we already knew was going on, but we were off by like a factor of 2 when we used Newtonian Newtonian gravity. When he used his gravity, he got exactly the right answer. So, and then back in either 2015 or 2017, I think it was September 15th, which is why I have a hard time remembering the year. We finally, 100 years later, have confirmed two other predictions of Einstein, which is the existence of gravitational waves or gravitational radiation and the existence of black holes. So Einstein's still being proven right now. Okay, you guys are free to go. We ran about 30 seconds over. I did have my alarm set, so I was keeping an eye on that. But like I said, anytime I run over, you're welcome to leave right on the time. It's not offensive to me. I get it. But you're also free to tell me. So have a good one, everybody. Keep an eye on your email. I should be making a practice test, and actually maybe 2 practice tests and a test available before the weekend. And they will be due 7 days thereafter. And then next week, I'll have the redo midterm posted as well, and you'll get at least 7 days there. But I'm going to give you basically all of Thanksgiving break plus maybe till Wednesday after. So keep an eye on your emails, folks. Have a good one. Stay safe. See you next week.
Have a good day.
Thank you, Jamie.
I had a question
Go for
quickly. Next week, is there going to be a meeting on Wednesday?
I think our classes are off Wednesday, so that would be no. But let me double check the academic calendar. I got it right here in front of me.
Yeah, because that's day before Thanksgiving. I'm just curious.
November 23rd and 27th were off. I think the 23rd is Thursday, so they might be just giving us Thursday and Friday, it looks like. 23rd. November 23rd, Thanksgiving break.
Yeah, the 23rd is a Wednesday. So
yeah, so we're off. So no, you won't be meeting Wednesday.
All right, cool. All right, thank you.
Thanks for forcing me to check that because I needed to know too.
Yeah. All right.
See you, Joseph. William, Alvin, anybody? Y'all have any questions for me?
Yeah, I had a quick question.
Go for it.
So the test you're talking about next week, which one is that?
That's just going to be on on either 2 or 3 chapters that we've covered since the midterm. I've just sort of given you a little bit of a hiatus, not necessarily intentionally, but because I was really trying to figure out what I wanted to do about the midterm. So we need to catch back up. Ideally, I'd like to keep my test at 2 chapters per test. But in order to do that and fit them all in, I might need to go 3 this time. I think we finished on was it chapter 6 that was the last test chapter we did in the midterm? So this should be at least 7 and 8, but maybe 7, 8, and 9.
And then is this one, you might have said it, but I was confused about this and then the midterm redo. Is this one Respondus or is this?
No, this is just an online. The retest midterm will be a Respondus one like that, but all these other ones will just be online where you're allowed to use your book, your notes. You're even allowed to do Google searches. You just got a limited amount of time, but you get multiple chapters.
Okay. And then one last question, sorry. So I was looking at the grade book and I'm not sure if it's supposed to be, but there was one of the extra credits that was labeled
one of the extra credits in the wrong category, so it's counting already.
Yeah, it's counted as homework. So it's,
so what I do with that, it's supposed to be each extra credit is going to count as a homework. But I'm supposed to increase the number of drop grades by 1 for each extra credit I did. So it's not that it's in the wrong spot. It's that I haven't increased the number of drop grades yet. But thanks for letting me know that.
Gotcha. Okay. So once that's increased, it'll just drop that.
Yeah, it'll fix that. Usually when I do it, I also go in and put in zeros on the extra credit assignments for anybody that didn't do them. So it might even go lower again and then pop back up.
Okay, I just want to double check.
No problem.
I know you probably covered it, but
that's cool. No problem. Yeah, Alvin asked, when do we get access to the video recordings? I usually am able to do this within an hour of class. Sometimes the internet goes slow and I won't get it done till the morning, but I very rarely have to wait till the morning. So it definitely should be within a couple hours from now. Anybody else? Eric, I saw you came back in. Is there any questions you had?
Yes. No, sorry, I'm stuck at a conference in San Diego, so I missed the beginning of this, and I wasn't in Monday. But my plan was not to redo the midterm because I think I got like a 96 or something. So I'm okay with keeping that.
That's cool. You don't have to. I would say take it just for the extra experience, but you're really not required to at all. I'm going to give you the higher of the 2 anyways.
I'm more worried about the assignments I missed that were due a couple nights ago.
I got you. Yeah, I get you. Yeah, the more practice you get, the better. So definitely if you've missed homeworks, it's better for you to make those up to just get, more problems under your belt. Anyone else? All right. Well, I hope y'all enjoyed the discussion today. We didn't get to solve too terribly many problems, but I think I explained a lot. So hopefully that'll help you. And this should be up pretty soon. Like I said, it usually takes about 30 minutes for it to download to me and process. And then it takes about 30 minutes to an hour to upload to YouTube. So check it out. Of course, the notes are up usually within 5 minutes from the class ending. So if no one has anything, I'm going to go ahead and say bye-bye.
Wait, quick question.
Yeah,
you said something about, you said we're retaking the midterm.
Everybody's allowed to retake the midterm. And I'm only going to count the higher of this grade or the one you already took. And I still have the rule where if you do better on the final, I'm going to replace your midterm with the final grade.
Okay, thanks. When is this due?
I was telling everybody you're probably going to have a test that's going to come up in the next day or two, and that'll be due probably Wednesday of next week, definitely 7 days later though. And then the actual retest midterm will open up just before Thanksgiving, and you'll have all of Thanksgiving until maybe Wednesday after Thanksgiving.
Okay, thanks.
No problem. You'll do this. It'll be Respondus lockdown browser with the monitor on it. So you'll need a camera, computer with a camera, or you'll take it to a testing center or something.
Thank you.
No problem. See you, Alvin.